Hello everybody, this is Ruth Stuckey here with Module 7b for 50HC, in which we're looking at non-ionising radiation. We have our usual copyright warning. The objectives for this module are that on successful completion you should be able to identify and describe the nature and sources of various types of non-ionising radiation, access, interpret and apply information about the toxic effects of selected non-ionising radiation hazards, identify and describe routes of entry, identify the appropriate requirements for and use of expert assistance to reduce workers' non-ionising radiation hazard exposures, and manage related dose and health impacts. And develop, evaluate and maintain a safe system of work based on accurate information relating to workplace control. When we're talking about non-ionising radiation, our focus is at the other end of the spectrum, so to speak, from the ionising radiation. It includes radio waves, microwaves, infrared rays, light rays, ultraviolet rays, and UV. This end of the electromagnetic radiation is distinguished from the ionising end in that the different wavelengths and the different amount of energy that's transferred. You've got constant speed, constant environment. Radiation with a longer wavelength would have fewer waves passing through it in a given time and be lower frequency. And the ones with a shorter wavelength have more waves passing in a given time and they're the higher frequency. But at the moment we're talking about the lower frequency ones. And this lower frequency also determines their ability to travel through objects and the heating effect, so less hot, so to speak. Electromagnetic radiation of wavelengths greater than 100 nanometers, therefore the UV, visible light, IR, radio frequency and ELF, infrasound, ultrasound and laser are all classified as non-ionising radiation. This spectrum is often divided into four major classes for categorization, each class having a lower frequency range than the previous one. So the highest one in this group being the optical, which includes UV, visible light and IR. Then we have the microwaves and radio frequency, then the very low frequency, and the class with the lowest frequency being the extremely low frequency. I'm not sure. So we'll start off with ultraviolet radiation. The sources of ultraviolet radiation, this is wavelengths from about 100 nanometers to 400 nanometers, and from the viewpoint of biological effects it's divided into three components. UVA, or black light, UV ranges from 315 to 400 nanometers. UVB, also called erythritol, UV ranges from 280 to 315 nanometers, and UVC, which is often called germicidal, UV ranges from 100 to 280 nanometers. The sun's a major source of UVA and UVB radiation. The atmosphere absorbs solar radiation of wavelengths less than 290 nanometers. The sun is the source of UV and can of course be work or non-work related. The major industrial source of UV is electric welding operation. The biological effects of UV are the wavelengths have potential effects on humans when they range from 180 to 400 nanometers. The potential health effects include damage to the skin, causing erythema, reddening or burning, and skin cancer. The most damaging wavelength is around 270 nanometers. The eye, causing cataracts, keratosis and conjunctivitis, and the immune system, which is about suppression. Skin cancers include the very common but rarely fatal basal cell and squamous cell carcinomas, plus the uncommon but often fatal, in less than 20% of cases, melanoma. The number of deaths from melanoma is roughly double that from all other skin cancers. Other effects on the skin include premature aging and photosensitive reactions. A large number of chemicals enhance the the erythermal response to UV and visible radiation, and examples include coal tar products and antibiotics. The eye may be damaged as the conjunctiva, cornea, lens or retina, depending on the wavelengths of the UV radiation. UVB and UVC absorbed in UV radiation is measured by using a photoelectric sensor. The acceptable quantity of the radiation depends markedly on its wavelength. Exposure standards are set to protect the eye and the skin. Two standards apply, one for UVA for skin and one for UVB and C for skin and eyes, and one for UVA eyes. The standards are primarily dependent on the wavelength of the radiation and the spectral irradiance or energy of that radiation. And you can find these standards in the ARPANSA 2006 Radiation Protection Standard for occupational exposure to ultraviolet radiation, and that's easily found in the ARPANSA website. Control of UV radiation should follow the hierarchy of controls, so engineering controls based on containment or isolation of the sources of the radiation and the use of appropriate filters to absorb it. Outdoor workers should use existing shade or rig temporary shade. Administrative controls include warning signs, minimisation of exposure time, and training of operators. PPE should be opaque to UV. If it's opaque, then we move on to near-infrared radiation, or IR, and visible light. In occupational hygiene, a distinction is made between near-infrared radiation and longer wavelength infrared radiation. High-powered sources of visible and non-infrared radiation include arc lamps and welding. The biological effects of visible light and near-infrared, which is 400 to 1400 nanometers, pass through the cornea and lens and are then focused on the retina. The focusing properties of the eye may produce an image on the retina many times brighter than that of the sun, which can result in gross retinal damage. Measurements are made with photoelectric devices. Control is achieved using the hierarchy of engineering control, administrative control, and PPE. Engineering controls may involve eliminating, substituting, or shielding. Administrative controls may involve modified work practice, segregation, or distance, and PPE involves the use of suitable glasses, goggles, or face shields. The normal reflexes such as pupil contraction, blinking, and aversion to pain or discomfort usually provide an adequate. Then we have long wavelength infrared radiation. In industry, sources of wavelength longer than that of infrared radiation include furnaces, hot plates, and lamps to aid in the curing of paints. The biological effects of the longer wavelength, which is more than 1400 nanometers, infrared radiation are essentially thermal. Heat stress, fire, skin absorption, or eye injuries such as glass blowers, cataracts, and corneal injury. Long wavelength IR is absorbed by the cornea and does not penetrate to the lens of the eye. Instruments for measuring long wavelength infrared radiation are heat sensing devices. These may incorporate thermistors or other temperature-sensitive electronic components. There's not yet any regulatory exposure standards for IR. The exposure standard for long-term protection against cataracts resulting from excessive heat load due to long wavelength IR is 10 milliwatts per square centimetre, and that's in AS2243. Control is available using shielding, distance, and appropriate filters for eye. Lasers. Laser is an acronym for light amplification by stimulated emission of radiation. They may generate UV, visible, or IR radiation, and so are not from a distinct band of the NIR region, the non-ionising radiation region. Special hazards from lasers arrive from their high power density or their intensity and their low divergence as the beam narrows over extremely long distances. The beam remains narrow over extremely long distances. So these are both at intense and low divergence and therefore can focus on a very small target. Laser products are grouped into 4 general classes and must be labelled with the appropriate Class 1 up to Class 4 label. And you can read more about these actual classes in both your readings. There's a little quote there at the bottom about the energy being concentrated into a small area and how efficiently it can carry over large distances, which is why they can be a real problem in terms of OHS. Applications of lasers including communications, entertainment, laser printers, barcode readers, surveying, cutting and medical procedures. Lasers are used extensively in the construction and health industries for drilling holes in metal and in teeth. The application of lasers continues to increase in occupational environments. According to the Australian Radiation Protection Nuclear Safety Agency, or ARPANSA, light emitted from lasers. The biological effects of lasers depend on their wavelengths. Their UV and short wavelength lasers produce photochemical effects, whereas other lasers produce heating or burning. As with UV, visible or IR sources, the eyes and skin are at risk. For high-power visible lasers, the blink reflex may not be fast enough to provide protection. Where the eye receives minimal exposure to a laser beam, temporary blindness may occur, similar to that caused by a photographic flash. If the flash blindness lasts for more than 1 hour, permanent damage is likely. The measurement of laser output is performed only by manufacturers or radiation specialists. The major mechanisms for control of lasers are engineering and administrative, although PPM may be used. Lasers must be labelled with the appropriate class, and for each class there are maximum powers and emission limits. Depending on class, the user may need to implement engineering controls such as interlocks, special rooms, barriers, and beam termination. Administrative controls are discussed fully in the Australian standards AS2211 and 2397, and other controls include display. The next group is radio frequency, or RF radiation, which is often known as microwave, or includes microwave and radio wave. Radio frequency radiation, RF radiation, ranges from 30 kHz to 300 GHz. Within this broad range there are several regions. RF from 300 GHz to 1 GHz is known as microwave, and RF from 1 GHz to 30 kHz is known as radio wave. Both microwave and radio wave radiation can induce electric currents in conductors such as metals. These currents may cause heating of the conductors. Examples of the application of RF include heat treatments of metals, hardening, smelting and welding, heat treatment of dielectrics, heating wood, heating food products, heat sealing of plastics, radio and television receivers, and medical applications and microwave ovens. The biological effects of radio frequency radiation have the capacity to heat the human body. This is similar to the way in which microwaves heat food in a microwave oven, and thermal damage may occur if the intensity of radio frequency radiation is too high. Although suspected, there is no conclusive evidence that long-term exposure to radio frequency radiation induces cancer at this point. The measurement of the energy level of RF radiation is based on an assessment of either the power flux density, the electrical field strength, or the magnetic field strength, and consideration of the position of an exposed person with respect to that field. In order to cover the RF range from 300 GHz to 30 kHz, more than one detector is required. Some microwave detectors display the measurement in terms of the power flux density, or the wave in meters squared. The electric field of RF is detected in instruments equipped with straight rod serials. The electrical field induces a voltage, which is then measured by the electronic circuitry. The general approach to controlling exposure is shielding, things like metal screens, as well as other engineering controls. Time, extra low frequency radiation, or ELF. The extremely low frequency radiation is most commonly 50 Hz. And it's radiation from electrical conductors. Initially, concern regarding ELF radiation arose from overhead power lines, but now it tends to focus on ELF from wiring in houses and offices, which is alleged to be associated with increased risks of leukemia. Biological effects, if we assume that electrocution type shocks are avoided, there are effects such as the tingling of the hair and magnetic fields at frequency around 15 Hertz appear to have biological effects and have been used to enhance the healing of bone fractures and wounds. So some of these effects are actually used positively. A 50 Hertz electric field does not penetrate the body, but the magnetic field does. Therefore, any undesirable health effects are now thought to arise from the magnetic rather than the electric field. The strength of a magnetic field is related to the current, hence arc welders or even hairdryers, rather than voltage power lines, and these are claimed to represent a risk to health. However, the evidence for such health risks is far from conclusive. At this stage, Australian radiation authorities do not regard chronic exposure to 50 Hertz electric and magnetic fields, such as power lines at the levels commonly found in the environment, as a proven risk. However, if you have a look at some of the WHO, ELF measurement is made of both electric and the magnetic fields using detectors as described for RF radiation. These guidelines are aimed at preventing immediate health effects resulting from acute exposures to these fields. The recommended magnetic field exposure limits for members of the public 24-hour exposure is 1000 milligauss, and for one occupational exposure over a whole working day is 5000 milligauss, or 0.5 millitesla. Control is relatively simple for electrical, but not for magnetic fields. People inside a car or a metal cage experience zero electric field from an external source. Shielding from the magnetic field is normally impractical, and redesigning of wiring can lead to cancellation of these magnetic fields. So, for example, if you find that there's an unacceptable magnetic field around a electrical station within a work environment, what you can do is either put shielding around that actual station, or you can move people away. And these are strategies. There's a couple of other radiation sources of interest that we'll discuss briefly, and the first of these is visual display terminals. Over many years, media reports have claimed that operators of VDTs associated with a range of different equipment and computers have an increased risk of brain cancer because of the magnetic field emissions from their VDT. And going back further, there used to be discussion around whether VDTs induced spontaneous abortion as well in pregnant women. VDTs emit both electric and magnetic fields. There's no unequivocal evidence for adverse health effects resulting from prolonged exposure to weak electric fields published to date. The only monitors that use a cathode ray tube, the same as a television, generate magnetic fields. Flat screen displays will not. At present, scientific opinion is divided as to whether chronic exposure to weak magnetic fields is hazardous. ARPANSA is a part of the Commonwealth Government and circulates information about public health regulation services on their web, and we've already given you advice about access to that website and their advice. Their current advice concludes that above health effects are not supported by either epidemiological or animal studies. The emission levels used in Australia are less than the relevant recommended exposure limit. The exposure of VDT operators has decreased markedly over the years because of modifications to the design of VDTs, leading to reduced magnetic field. Mobile telephones are probably much more contentious these days, and there's more dispute in the scientific literature. But basically, this is from the ARPANSA website. There's no clear evidence in the existing scientific literature that the use of mobile phones poses a long-term public health hazard. although the possibility of a small risk cannot be ruled out. There's a big project going on at the moment, which is the Interphone project, which is a multinational series of epidemiological studies testing whether using mobile phones increases the risks of various cancers in the head and neck. A pooled analysis of all the brain tumour results has suggested no overall risk for moderate mobile phone use by adults for up to 10 years. Pooled analysis of all the brain tumour and acoustic neuroma results have suggested no overall risk for moderate mobile phone use by adults for up to 10 years. The pooled analysis suggested the possibility of an increased risk of glioma and acoustic neuroma in the group representing individuals with the highest cumulative call time. However, limitations on the methodology prevent conclusions of causality being drawn from these observations. The pooled analysis also pointed out that the possible effects of long-term heavy use of mobile phones requires further investigation. It's worth having a look at this information on the website because there are definitions of high users and moderate mobile phone users I find fairly interesting. And I think a whole lot of this is still developing because really we haven't got any long-term exposures in terms of high numbers in the population. So this is a watch and wait one as far as I'm concerned. I think that using hands-free is really important, but that has the use of mobile phones generally has issues, particularly with driving, whether it's hands-free or handheld. And this is going to be a watch and wait one for a lot of people. And I think it is worth watching and waiting. And one of the things that's been raised is that we really don't know about what the risks are to younger users. And the data related to children is certainly being collected. This has been a long module and it's quite complex, and we've covered various types of radiation, and with the last module, ionising and non-ionising radiation, outcomes, exposures and workplace issues. It's a very complex field and you don't need to have an understanding of all the information that I've given you, but you do need to have a good understanding of the underpinning concepts in terms of identification, assessment and control. What we do need to know is when to bring in the appropriately skilled occupational hygienists or others working in this area, and we need to know how to use that expert opinion. We need to know what the different types of ionising and non-ionising radiation are and where they fit on the wavelengths in those broad terms, going back to that diagram that I've had at the start of module 7a and 7b. And we need to be able to get the right support to help us understand better and then implement appropriate controls. The other thing we need to know is where to go and find an evidence-based to support our interventions. And like many areas of OE, then we have our references. And that's the end of this module. Thank you very much. Cheers, bye.